Hello. So we can all agree that understanding the cache performance of a program is important. Today, this is difficult in MLR. Profiling is expensive and is also non-deterministic. We present MLR Mem Info, which is a static analysis tool that efficiently and deterministically determines the cache miss rate of a program. So let's start with an example. We start with an example of 2D matrix multiplication. We have two memrefs, A and B, and we just matrix multiply them to get a new memref, C. So let's transform this into apply a transformation to this to optimize this. So we get the final program, which has two memrefs, A and B again. We transpose B, and then we pack these A and B transpose into 4D memrefs such that they're tiled. Then we apply matrix multiplication transpose on them, and then we unpack them to get the output memref C. This is a common transformation used in optimized linear algebra libraries like RUI, and it's called matrix multiplication transpose 4D. So if I ask you to look at the final program, and I ask you, is the cache miss rate of this program intuitive to you? Can you just look at it and tell me this? And how long would it take you to profile this program? Now, this was a small program. What about if we look at even bigger programs? We look at something like the transformer block, which is used in transformers like BERT. I take this matrix multiplication there, and I transform it using the transformation we talked about before. Now, I ask you the same thing. What is the miss rate of the final program? Is it intuitive to you? And if I ask you to profile it, how long would it take you? Remember, you have to run the whole BERT program each time you want to get the cache behavior of the program. The cost of data movement is not intuitive, is what we understand. It's not easy to determine those things. So we take another example. We have input memref in, and I apply two kernels on it, kernel 1 and kernel 2 sequentially, and I get output memref out. So I decide that, hey, I want to optimize this. So I choose, like, I want to either fuse loops or I want to tile this. And you are going to decide this. Maybe you're a person, you're an auto-tuner, or you're a compiler, and you just want to decide which one to apply. And you ask yourself, which one of these has the better cache locality? Is it easy to find out? Is it understandable? And it's not, so you resort to profiling. So we did a similar thing with BERT. We took BERT and took an unoptimized version of it in Linalg and compiled it down with LLVM with O3 optimizations. And it took us 18 minutes to just run it and get the cache numbers. And this is, you're just forced to take a coffee break. So instead, what if there was a tool that could just tell you the cache numbers in just 12 seconds? Now you could run multiple iterations of different transforms in the same session, and you could try different transforms and find out which one works for you the best. So this is where MLR Mem Info comes in. And let's see it in action. So we take MLR Mem Info, and I pass it the cache parameters of my L1 cache of my machine, which has 512 cache lines and 8 set associativity. I run this on the original matrix multiplication code that we had. So it gives us some output, and let's focus in on something that matters to us. It tells me that this Linalg.matmul operation that I see here accesses 99.97% of all the memory accessed by the program, and it has a miss rate of 25%. Now, I look at this, and I understand, OK, this is bad. So I apply the matrix multiplication transform we talked about before, and it now tells me that, hey, when you apply this, it still has similar access to this percentage with the new operation Linalg.mmt4d, but it has a miss rate of 1.7% now. So I can actually look at that optimization, and I can look at my tool. It can tell me that it does improve cache locality, and it does this in less than 150 milliseconds. So we also do this with the BERT matmul we looked at. I focus it, it runs it on the whole program and determines it for each statement, but I focus in on the matmul that we talked about before. And it gives me similar thing. It gives me that it accesses 0.6% memory of the whole, memory accessed by the whole program, and it has a miss rate of 26%. Yeah. So for 0.6 is a lot for a big program, and it tells me that you could improve the miss rate here. So MLR Mem Info understands that you want to do transformations. So if your transformation annotates that which operations were modified, MLR Mem Info understands that it does not go and recompute the whole thing. It only recomputes the new operations and the old operations that were affected by the addition of new operations. It can detect that using some heuristics that we use. And we took a number of transformations on BERT, and we ran them all. We found that on average, it took us 500 milliseconds to recompute things, which is instant. You could, as a person or auto tuner, you could try so many more variations versus the 18-minute coffee break. So this is how the output looks like if you do a transform. So it tells you the original miss rate, which was 26.5%, and the access percentage. And it tells you the new miss rate, which is now 0.19%. So I can prove it on networks like BERT or like some other network that, hey, my miss rate actually improves, and I do it in 500 milliseconds, which is great. So now I invite Arjun to talk about our algorithmic foundations.
Thanks, Kunwar. So before we go into the details of the algorithm, we should first understand how the caches that we're modeling actually work. So our MLR Mem Info models LRU caches, which are caches that have a least recently used replacement policy. So let's see what that actually means. So let's say we have a stream of accesses coming in. Initially, the cache is empty. And then you access a location A, a B, and a C. And all of these are going to end up being misses because, I mean, you're accessing them for the first time. There's no way that they cannot be misses. And they come into the cache, and now we have these in the cache. Now, if you access C again, it's going to be a hit because, I mean, it's still in the cache. Now, if you go and access a different location, D, it misses because it's for the first time, and it comes into the cache. And now, let's say that the size of the cache is limited to only 3 locations. So we have to decide to bring in D. We have to decide to which other thing we're going to evict or get rid of. And the point of the least recently used policy is that we're going to get rid of A in this case because that's the one that was accessed least recently. So if you keep going, access D a couple more times, they're going to be hits. And now if we access B again, it's still going to be a hit because B was accessed sufficiently recently that it was still in the cache when we accessed it. And now the thing with the LRU policy is that this actually matters that we now access B again. It affects the cache state. So here, B has moved from the back to the front of the cache because it's now the most recently used thing. And if we now access A again, it's going to miss, and it's going to bring A into the cache. And what's going to be evicted is C. Whereas if we hadn't just accessed B, it would have been B. So if we look at the pattern in the cache state that appears over here, you basically see that if the cache has 3 elements in it, then the cache state is just the 3 unique locations that were accessed most recently. For the sake of this illustration, we ignore cache lines in case anyone is thinking about that. Yeah, so this is how the cache state is going to be. This is actually quite a simple cache state to think about. It's just the 3 locations that were most recently accessed. And now let's think about how we can have misses in this policy. Now, firstly, if you access something for the first time, it's obviously going to be a miss. There's no way that caching can help you there. And secondly, if the most recent access to the same location was a really long time ago, then it doesn't make sense to keep it in the cache the whole time. So in that case, again, in LRU, you're going to have a miss. So let's look at something more specific. So in this case, if you look at the second access to B, it's going to be a hit because there were only 2 unique locations accessed between this B access and the first B access. So we brought in C and D into the cache, and then B was still there. So B was a hit. Now, if you look at A instead, we brought in B, C, and D into the cache. These streamed through the cache and pushed out the A. So now A was pushed out, and it turned out to be a miss. And this is really what governs whether something is a hit or a miss under the LRU policy. So we need to find out when the most recent access to the same location was and how long ago it was. Where by long ago, we don't mean the number of accesses. I mean, here between B and A, there's only a difference of 2 accesses. But what matters is that how many unique accesses you have. So here there's a bunch of C's and D's, but they only count, like each C and D counts only once. Now, this was our understanding of the cache. Now we need to write some kind of algorithm down which is going to exploit this to model and predict it. Now, there was some earlier work in the literature on this, but how they work is, I'm not going to go into the details, but basically you set up some sets A, I, and S that you take the whole program and you turn it into this gigantic formula in a Pressburger logic, and then you do some various manipulations on them. You create these sets L, again, F, E, B, N, D, F again, and you find out the compulsory misses. So it kind of ends up like this meme here. I don't want to make fun of it too much, but basically you start with a huge formula and you do a whole bunch of manipulations on it, which does tend to blow up when the size of the program is large. So these models were evaluated mostly on single kernel benchmarks, in which case it wasn't an issue, but we want to scale these to large programs like BERT that Kunwar talked about, and then you really have a blow up. So to look at it in more detail on an actual program, let's take an example. So this is an example program. Like first we access all the locations in A, 0 to 499, all locations in B, and then C again. And finally, we access a couple of single locations like C0, B400, and AX. Assume that X is inbounds here. Now, the first three loops, they're going to be misses because, again, you're accessing these arrays for the first time, assuming no aliasing and stuff. So that's one thing. Now, what we want to do instead of starting with this, converting the whole program to a formula, is we want to sort of use some compiler techniques. So if you think about what a most recent access is, which we came up with by analyzing the LRU, it's really just like the dependence. So we use what's called polyhedral value-based dependence analysis. But anyways, we used some kind of dependence analysis to figure out for each access when the most recent access to the same location was. And in this case, these are the first accesses to those locations, which is equivalent to saying like there's no dependence. And so they're all those compulsory misses that we talked about, which are the first accesses. And now let's look at something else. Let's look at the C0. So here, the most recent access was in some iteration of that loop over there. And for B, it was in some iteration of that loop, and then for A, some iteration of that one. Now, let's see how far these are. So here, C0, it was accessed in iteration 0 of that loop. So there were the accesses in between are C1 to C499. So that's 499 of them. And that's less than, so let's assume a cache size of 512, which is typical for like an L1. And again, ignoring cache lengths, assuming the cache length size is 1. Now, so this is going to be a hit. And now if we go to the B one, then you can see that there's 2 loops in between, but they access the same memory. So in total, there's 500 unique locations that these access. And now if we look at B400, it's accessed in iteration 400 of that loop. And the accesses in between are from B401 to 499. So these are 500 plus 99 accesses, which is greater than the cache size 512, which means it's going to be a miss. Now, if we look at A, now our model cannot actually like analyze something where there's these unknown variables like in all cases, but in this case it's actually possible. So I just want to illustrate this because it's really the crux of our optimizations. So if you look at this and you try to count how many unique accesses there are in between, you see that the 2 C loops, there's a 500 there. And then you look at the B loop, there's again an extra 500 coming in. Now it doesn't even matter like which iteration of the A loop we found the dependence in, because B plus C is already 1,000, which is way over 512. It's going to be a miss for sure. So in this case, it doesn't even really matter. We could like change the loop in some arbitrary way. Like it won't affect the cache miss rate. It won't affect the cache performance of that load A statement. Like we could add like other statements. Maybe we add statements in such an arbitrary way we don't even know which statement in that loop the dependence is to. It still doesn't matter. Like as long as like we have at least 1,000 things in between, and none of those things have the dependence, we know it's going to be a miss. So we can change it to B. Maybe it doesn't even access A. It's still a miss. Now it's the different kind of miss, which is it's a miss because it's the first access. But either way, if you cross this threshold of 512, you know it's going to be a miss. It doesn't even matter like what, we don't even have to look at that loop. So that's really like one of the core optimizations we have, which is that you don't have to look beyond a certain point. And the earlier algorithms, how they would work essentially is when you operate on these formulas, implicitly you end up checking all pairs of statements for these dependencies, which is quadratic. But for us, we know that for a statement, you only have to check a certain fixed distance above, which is dependent on the cache size, which means it's more like a linear thing. And you can see these speedups in practice on the plots as well. It's not like just theoretical, but it just means that we're much faster on large programs. And the other advantage of this optimization is that, like Kunwar talked earlier about incremental recomputation, which means that, let's say you transformed like the first loop in some way. And now we can efficiently recompute the cache performance of the entire thing, because we know that no matter what changes you make over there, the last statement's cache performance is not going to be affected. So we don't need to do any additional computations. We just like keep it the same as it was before. It doesn't matter, like you can have anything there really, and it stays the same. So the way it works, the algorithm, is that you start at the modified region and you keep going down, and you see, so once you cross the B loop, there's 500 accesses there. You cross the C loop, you reach 1,000 unique accesses. Once you reach 1,000, it's greater equal to 512, and everything after that is not affected by this modification. So if you had modified this first loop here, you would only need to really check 3 loops again. And everything beyond this threshold has the same performance as before. If you look at it in detail, you can see that like each of these statements has a dependence within the region that was not even modified. And the thing about LRU, as we talked about, the only thing that matters is when was the most recent access to it and what happens in between the most recent access and that access. So in this case, all of that is the same as before. Nothing has changed. So we don't even need to recompute anything here. Now the AX statement is a little different. Its dependence is outside this like same region. It goes into the modified part. But in this case, what happens is that we know it was a miss again because it goes beyond that threshold that we talked about, beyond 1,000. So for that reason, we only need to recompute results for this like blue block over here, which is the only part which can possibly have different performance. Of course, you also have to compute the changed part, but that's not included here. Yeah, so this is really a constant amount of recomputation that you have to do, which is down from quadratic in like the original algorithm, which is, I think, pretty cool. Yeah, so that was the algorithm. Now let's look at the performance. So, of course, we care about accuracy. Otherwise, there's no point like if you compute it however fast. So this is on a single kernel benchmark called polybench, and there is one outlier here, which is due to associativity. So our model does support set associativity, but we're not going to go into the details of that here. The outlier there is because of running the model on a fully associative setting. But essentially, you can see there's a good trend. Like the measurement is and the predictions match quite well. If you look at larger neural networks, it doesn't look quite the same. So it's not a 45-degree like you might expect. But still, we believe that this shows that there's a correlation between the prediction and the measurement, which is sufficient to give you a signal for optimization if you're an auto-tuner or even like a performance engineer. This again has a couple of outliers, but we're working on it. Finally, let's look at the speedups or like running a profile. So that's like these are like a bunch of torch vision neural networks that we lowered down to Affine. And like the geometric mean speedup is 5x, and it can be really high for like 2 orders of magnitude on some networks. And runtime wise, it's like 25 seconds geomean and 2.2 seconds if it's multi-threaded. So one of the advantages of our model is that because every statement was independent, it's actually embarrassingly parallel. Like you can run every statement in parallel, which was also not possible with earlier models. And finally, the recomputation for various reasons is on different networks. But the interesting thing here is that it only takes like 100 milliseconds on average to recompute after like changing like a single random loop in the program. Now, obviously, if you change the entire program with an entire different program, you're not going to get an incremental recomputation. So what we mean is that you locally change like one loop, and each of the dark green bar is how long it takes for the initial computation, and the light green bar, single threaded, and the light green bar is, each of the light green bars is how long it takes if you change one of the loops. So it turns out that some loops are harder, more complex than others. So there is this one loop in AlexNet which actually is most of the time. But on average, if you change like some random loop in the program, then you probably will spend like 100 milliseconds to recompute. So that's the end of the talk, really. We presented a memory model for Linalg that tells you the access percentage, which is to say how much of the access in your program are in a particular operation, tells you the miss rates predictions, which it runs in like 2 or 3 seconds 16 threaded, and maybe 25 to 30 seconds single threaded. And we supported incremental recomputation using a new algorithm that takes advantage of the fact that you need like temporal and spatial locality to have any effect on cache performance. And therefore, we get these recomputations in 100 milliseconds on average. Thanks.
Thank you, Kunwar and Alashan. We have time for a couple of minutes before our next talks. Joey.
Thanks, Jeremy. Thanks, a very good talk. Just asking, does this handle multi-level of a cache hierarchy, like L1, L2, L3 cache, and also the complexity of inclusive cache and non-inclusive cache, something like that?
Yeah, that's a good question. So these things, yeah, there's this huge zoo. So we can handle the caches that are present in today's like Intel and AMD CPUs that I've seen, which means that it's an inclusive set associative cache we can handle. We can't handle exclusive set associative, which is quite weird and also not common. And various other odd configurations are not supported. But the most popular one is the inclusive set associative, which we can handle, yes.
And we can also handle multi-level caches. We cannot handle like a shared cache like L3 because it's hard to determine.
Yeah, I mean threading is weird,
but we can determine.
L1 and L2 is fine.
We have tried it on like AMD and Intel caches. For L1, L2, it works.
Hey, thanks for the talk. So you said at some point briefly you use polyhedral dependency analysis as a underlying thing. Is that true?
Yeah.
And then you said our thing is linear O of n. Polyhedral value analysis is exponential, and that is actually effectively the same math you made fun of 2 slides earlier. It's exactly that.
Yeah. So, like I said, I mean, I did say I don't want to make fun of it too much, but it really depends, like, because when you have like neural networks, the loop structures are really simple, like they tend to be hyperrectangular, and then like it's true that if your sets become arbitrarily large, then you can have crazy blobs. But the entire point of our thing is that because you do this AST thing, you only look at like a single statement and another single statement somewhere. And again, like if you had arbitrary loop structures, I agree that it's exponential. But like, I mean,
that brings me to my second
hyperrectangular.
question.
Sorry?
So you only, like all of your examples here have constant bounds. Do you allow parametric bounds? Because I mean, a lot of your reasoning.
No.
We do not allow parametric bounds, and like our workloads, like neural networks do not have them, so that's why it works well also for us.
Okay, I mean, fair enough. You can. I mean, it's a fair point to say no, we don't. That's good.
Yeah.
But the whole point of all of that before, and also why the mass before explodes in reality is parametric bounds. If everything is constant, those are just very easy computations.
No.
Using that math also, you cannot do parametric bounds.
Oh, sure.
No.
Oh, yes.
No.
So
like,
you can do dependence
We agree
analysis.
to disagree.
You can do dependence analysis, but you can't do the cache miss estimation.
I think
If you had
there's a
parametric
discussion
bounds.
to be had outside here. I think so thank you. We've got prepared for an exit talks. Thank you. I know we're out of time, but Kunwar, Arjun, thank you. Great talk. Excited a lot of conversation and discussion. I'm sure that will carry on outside in the discussion rooms. I can't help feeling there's a need for a round table later today. Okay, thank you all very much. In a couple of minutes, we'll have our quick talks. Can I just ask for the remainder of our quick talk speakers to come up the front here ready for that? Thank you very much indeed.